Okay, so yesterday we had seen we had started actually sequential circuits. Okay, and we know that sequential circuits are where is the okay sequential circuits are a combination of combination logic and some memory part. Okay, okay, and we had seen some timing definitions that are critical, that are to be followed whenever you design a digital system. So at least these two equations should be followed. Okay, this one. So try to get onto the concept of these timing definitions: setup time, hold time, then worst case propagation delay, then contamination delay of combinational logic, and contamination delay of the register. These things are we had seen. Then there was a small example also. Then we had revised some topics that we are already aware of, that what are static and dynamic memory. And the main difference is that static memory uh, preserve the information as long as power is on. Okay, and dynamic memories depend on the charge storage on those parasitic capacitances. And we know that with time the parasitic capacitance lose their charge, so it needs to be refreshed at some regular interval of time, and that's why there is a need of clock signal with a minimum of frequency, at least some desirable frequency, so that the capacitors does not lose their charge. Okay, so and latches versus registers, latches are level sensitive, whereas registers or flip flops are edge sensitive. Okay, and there is a difference, huge difference, as when this is a latch and this is a register. Okay, when the same input is given to a latch and a register, then what is the difference in the output of latch and register? We can very well look at here. Okay, and this tells us that we cannot interchange latch with the register or with the flip flop. You cannot use latch in place of a flip flop and vice versa. So whatever you design a digital system, whenever you design, so take care of this. So whether you need a latch or a register for a particular circuit. Okay, so let's proceed further, and uh, then we will continue looking at some circuits, actually sequential circuits based on different logic styles. So basically, all the sequential circuits are having the concept of memory in that. In those, within those, we know this thing. And so, how to create a memory? The concept that is used for creating memory in the circuit is this uh, positive feedback concept. Okay, positive feedback concept. Okay, so and this is different from negative feedback. So remember, you had studied about negative feedback and positive feedback in your basic electronic subjects. So there, can you give me one example of negative feedback and positive feedback circuit? Negative and uh, positive feedback.
Op-amp is of negative feedback.
Okay, right. Let's see. Op amp is negative and positive feedback. Anyone?
Sir, scheme trigger is positive feedback.
Skin what?
Sir, scheme trigger circuit.
It's a
It is,
trigger.
yes, sir. It is
Okay.
based on positive feedback.
Okay. Anyone? Any else? Any other example that you had studied in your B, the first subject, first semester subject? You are remembering this oscillator? Oscillator. Do you remember this? It uses a positive feedback, okay, concept, and in op amp we generally use a negative feedback, okay. In oscillator we use positive, and we know that thing, negative feedback gives us more stability, that it increases the stability of the circuit, okay, whereas the stability becomes, less, uh, becomes weakens when we use a positive feedback. But here the gain rises continuously. It goes out of bound after a certain period of time, okay, ideally. But we limit this gain, okay, to a certain limit to make use of this these positive feedback circuits, okay. And negative feedback is a very well, thing that's used. You will see most of the time that negative feedback circuits are there, but there are some good applications where positive feedback concept is used. Okay. Now, this is one of the concept that is also used to create a bistable circuit. Bistable circuit will be having the memory as one of its property. Okay. So to create a memory, which feedback concept is used? Positive feedback concept is used. Okay. So look at this. Very simple. This is inverter one. This is I1 inverter one. This is inverter number two, I2. Okay. And if these two inverters are connected back to back, and the output of this inverter is again taken here back to the input of this first inverter. Okay. So this forms the simplest circuit having memory. Okay, two inverters connected back to back. So this Vi1 is the input of I1, VO1 is the output of I1, and Vi2 is the input of I2, and VO1 is equal to Vi2 because they are shorted. Okay, and VO2 is the output of I2, that is again fed back to the input of I1, which is Vi1. So VO2 is equal to Vi1, like this. Okay. Now, if we know the VTC characteristic for this I1, okay, this I1 VTC, and this is I2 VTC. Now look at here, I1 VTC, okay, is the curve between its input voltage Vi1, okay, and its output voltage VO1, okay, and we know that since this is an inverter, so output is inverted form of input. We are aware of this thing, okay. Similarly, this is the VTC of I2, inverter number 2, okay, and this is actually the axes are changed, okay, where y-axis is uh, having the input voltage of I2, and x-axis is having the output signal of y2 actually. So when you rotate this VTC by 90 degree, it will look like this. Okay, so this is the I2 VTC rotated by 90 degree, and this is I2 VTC the way in which we had seen in the module 2. Okay, now since why it is being inverted here is rotated here, because we are going to map this VTC onto this. Okay, we are going to combine this VTC with this VTC, these two VTC, and we know that VO1 is equal to VI2. Okay, VO1 is equal to VI2. So this is VO1 and this is VI2. So these two axes are same. Okay, so we can combine these two VTC in this format. Okay, and this becomes VI2, that is equal to VO1, and also we know that thing, this VO2 is equal to VI1. So this x-axis becomes VI1 is equal to VO2. Okay, and when these two curves are mapped onto each other, we get this kind of diagram. Okay, right? So when these two VTCs are mapped onto each other, so we get 3 points where they intersect each other: point A, point C, and point B. The point A and B lie on the axis, y axis, and x axis respectively, and point C lie in the middle. It is not lying on the axis, but it lies in the middle region between the axis. Okay. So this is what you will get when you merge these two VTCs for these two inverters. So let's see. Uh, so actually there are 3 stable operating points, which are A, B, and C, where these two curves are intersecting to each other. Okay, A, B, and C. And so it means that when your circuit is operating at these points, then the circuit behavior will remain stable. Otherwise, whenever you switch to any other region apart from these 3 stable points, the circuit behavior may not be stable, and it will keep on changing. And ultimately, it has to go and settle to some stable point. Okay, A, B, or C. So the stable points of operation are these one: A, C, and B. Okay. So this is the characteristic. You can see the you can characteristic curve for this bi stable circuit that was built from 2 inverters. Okay. So keep these points in mind. And using that concept, the more complex memories will be built. Okay, so let's start with the simplest memory, that simplest flip flop, and that we are aware of. This is SR flip flop. Okay, now this cross coupled inverter that we had just seen, okay, in the previous section, provides an approach to store a binary variable in a stable way. Okay, so just let me go back to this. Look at here. Uh, Suppose if this is a 0 here, so this is an inverter. So at the output of this, we will get a 1. Okay. Now this 1 will be feeding to this inverter, second inverter, and you will get we will get a 0 here. The 0 is again this connected to here. So the same 0 appears here, then 1, then 0, then 1, 0, 1, 0, 1, 0, 1, 0. It means that we see that the values are not changing. So it will keep on uh, these values for infinite duration of time. They will not change. Okay, and this is what is the concept of memory. That something lies there, some data remains there at a location for a certain duration of time. So we can say from this operation that this particular circuit is able to hold some information, is able to hold digital information. Okay, is able to hold the binary data, right? So that is what it says, that that particular thing gives us an idea, gives us an approach to develop more complex memory. Okay, so in the previous section, that provides an approach to store a binary variable in a stable way. Okay, but okay, this can store, right? This can store, but if what would we do if we need to change the values? Okay, because all the time the input will not remain same. It needs to be changed with the conditions, right? So it means that we need to control the input signal with time. So we need to have some external, some control circuitry, some control mechanism also, through which we can change or we can modify the input values, the input signals into the circuit. Okay. So that particular circuit is good enough to store the value, so it can just store. But what should we do? So in order to change or control the input signals, okay, because signals will not remain same with time, they changes, we know this thing, okay. So it means that that particular circuit is not good enough to work as a full-fledged memory, okay. So we need some extra circuitry must be added to enable control of the memory states, right? And one of the simplest thing is SR, or also known as set reset flip flop. Okay, so look at here. So this is these are two gates. This is OR NOR gate. So let me call this as NOR 1, and this is NOR 2. Okay. Now, in addition to their cross couple, they will always be cross coupled in nature. Remember this thing, and this cross coupling nature provides us, gives us the capability to store data. Okay, cross coupling means the output of one inverter or one NOR gate, one output of first stage or output of one element is connected to the input of next element, and the output of this element is connected back to the input of the previous element. Okay, this cross coupling is the reason behind giving us this memory characteristic. Okay, so this was there, we had seen in the previous two slides. Okay, but here we have two more inputs, S and R. Okay, and these provides us a mean to feed input signals into this circuit. Okay, so these are inputs with the help of which we can actually feed any kind of input signal into the circuit. It means we can change the input signals. Okay, so these are kind of, you know, giving us freedom to control the signal that we can feed into the memory part. Okay, and we know that inverter is having just one input and one output. We cannot have more than one input into an inverter. Okay, so it was not possible to use inverters here. So instead, what is being used here? A NOR gate, because in NOR gate we can have more than one input. So it is having a two input. So it's basically a NOR 2 gate. Okay, it's also having NOR 2 gate, the lower one. Okay, now we can also use other gates also here to build the SR flip flop. Okay, you might have seen the implementation using NAND gates also connected in a similar fashion. Okay, having inputs and outputs. Okay, so that's one thing. But here, remember when uh, these are the inputs S and R, okay, set and reset, and these are outputs Q bar and Q. Okay, and this is the simple block diagram having two inputs and two outputs. Okay, and this is the truth table for this SR flip flop. Okay, so there are some points regarding this that you may be aware of already, but we want the outputs to be complementary in nature. Okay, that is Q and Q bar should be complementary to each other. This thing is required. Okay, and SR, if SR is 0 0, we know that thing, the previous output is maintained. Okay, the previous output is maintained. If S is high, R is low, it means that S high means it's set means setting output high, so it will set the true output to high logic and the complement output will become low. Okay, and the third condition is S0 R1, so when reset input is high, it will reset the output, true output, to 0 and Q bar will become 1. Okay, this is fine. But the last state is a forbidden state in the case of SR flip flop, in the sense that if you provide S and R equal to 1, both 1, then you will find that Q and Q bar both become 0, which contradicts our assumption that we need Q and Q bar to be in complement to each other. Okay, so since these two values are not coming complement to each other, so we do not use this. We say that this particular fourth condition is a forbidden state that should be neglected, that should not be used when SR flip-flop is being used in a circuit. Okay, and look at here, we know that when when uh, uh, when because this is using OR gate here, a two input OR gate, okay, two input OR gate. So when this is 1, when one of the input is 1, okay, and if the other input is let's say 0, so what will be the output? 1 plus 0 is 1, invert 0, the output will be 0. And if the output input is 1 here, 1 plus 1 is 1, invert 0. Oh, no. So I want to tell one thing. So let's do it like this. So when one of the input is connected to 0, okay, and if the other input is 1, 0 plus 1, 1, 1 inverse 0, okay, and if the other input is 0, 0 plus 0 is 0, and 0 bar is 1, okay, right, okay. Now when one of the input is fixed at 0, okay, then it behaves like an inverter with respect to the other input value. Okay, so let's say when this is fixed, this input is fixed at 0, okay, now the output will be the invert or complement of the values that appear at the other input terminal. So if this is connected to 1, you will get a 0 at the output. If this is connected to 0, you will get a 1 at the output. So basically, because we needed an inverter, and inverter could not have more than one input signals, so NOR gate, NAND gates, a kind of suitable candidates which can be used to create a simple flip flop. Okay, so this is basically a NOR based SR flip flop. Okay, then and this is the uh, implementation showing in terms of transistors, okay, and that the previous was showing in terms of logic gates, and we know that ultimately all the things are or should be expressed in terms of transistors, because transistors are the basic building block of these digital circuits. Okay, and actually we had how many inverters? So we had two inverters. Let's say this was NOR 1, this was NOR 2, this S and R. This output was fed back here. This was connected here like this. S and R. This was, I think, Q bar. S and R, Q bar and Q. Q bar and Q. So this is Q bar and this is Q. Okay, so and here, look at here, look at the first part, this first part. Okay, so look at this section from here to here. We have one PMOS here. Okay, M2 is one PMOS, M1 is one NMOS, M6, M5 are also NMOS. So the pull-up network is just one PMOS, and in the pull-down network we have 1, 2, 3 NMOS. Okay, so it's a ratioed circuit example, ratioed circuit. Okay, it's not a completely CMOS logic, because in CMOS we have the pull-up network and pull-down network to be dual of each other. But here, in this case, in pull-up network, we are just using one single PMOS. Okay, so one PMOS as load and three NMOS as pull-down network, that is implementing logic. Now look at here is that we want a NOR gate. Okay, we want a NOR gate, and this is the input. This is the input. Input fed to the gate of this PMOS and this NMOS. This is the input. Okay, and output is taken at the common here. This is the output of this first stage. Okay, this is the input. This is the output, right? And this is basically Q bar, this point, Q bar. Okay, and here this one is the input to this first stage. Okay, power gone. Okay, connected. Right. Power is gone in the college. Okay. Anyways, we have this backup. So this is Q1 point, and this is the input to this first NOR gate. Okay, this one. So this becomes which point? This becomes S point. This point S. Okay. Now the output Q bar is connected back to the input of second NOR gate. Okay, and this is the second NOR gate. Look at here. The clock we will see further. Okay, we will see later on. This is one PMOS, and then look at here M3 and M4. M4 and M3 are forming one inverter. Okay, so for this time, focus here. M3 and M4 are forming one inverter. Okay, and you have here, since this is NOR gate, and in NOR gate we know that in pull down network the devices are connected in a parallel fashion. Okay, so M3 is connected in parallel to M7, which is actually the input R. Okay, this is for NOR gate, this one, lower one, NOR 2 gate. NOR means the two inputs should be provided to those two NMOS devices in pull down network, which are connected in parallel to each other. And this M3 is in parallel to M7. Okay, and this R input is provided here. Okay, and this S was provided here for this first NOR gate. And in the pull-up network, we have just one PMOS. Okay, and at the gate of these this PMOS and these NMOS is the input to this second stage. Okay, the second stage, which is coming from the output of first stage, that is Q bar. Look at here, this Q bar is connected to the input of this. So this Q bar is connected, shorted. Look at here, shorted to the input of the second stage, right? And this comes here. Okay, and the output is here Q. The output is taken at the common point between pull up and pull down, and this is the output node for second stage, that's Q. And this output Q is connected back to the input of the first NOR gate. So this Q is connected back to the input of the first NOR gate. Okay, so this thing is not S. Sorry, this is not S. This point is actually this point. This point is this point. Okay, and this S is fed here. S is fed here. Okay, so we have SR S and R two inputs here, okay, external inputs, and the output of first is connected to input of second. The output of first is connected to the input of second here, and the output of second NOR gate is connected to the input of first NOR gate. The output of second NOR gate is connected to the input of first NOR gate, like this. Okay. All right. So it is like this, and uh, we also know that we will need a clock signal. Okay, that will control the various devices. It is used for various reasons. That it provides a synchronism between various devices, and it also because control signal is a running 0 1 0 1 running pulse signal, so we can operate at a desired frequency at a desired speed uh, for this circuit based on the speed of control signal, the clock signal. Okay, so there should be a provision for providing a clock signal. So one clock signal should be fed into this NOR 1 gate and NOR 2 gate both. Okay, so look at here, one clock signal is fed here for NOR 1 gate, and the second clock signal is fed here for NOR 2 gate. Okay, and these two clock signals are same actually, and they will control the operation of this particular SR flip flop. Okay, so this is the simplest SR flip flop. Okay, drawn in terms of transistors. Okay, so and you always try to relate this particular diagram with this one. Okay, then it will become easier to draw and understand, right? Okay, then we see that in the pull down, pull up, we are having just one PMOS, that is sufficient enough. Okay, then so it means that if we had done this with the help of fully complementary CMOS, then we might have needed 3 PMOS transistors here and 3 PMOS transistors here, because there are 3 NMOS transistors present here in the pull down network and here. So in that case, we might have ended with 3 plus 3 6 plus 6 12 number of transistors. But here it gives us a compact circuit as compared to fully complementary CMOS, in the sense that it is using just 3 plus 3 6 plus 2 8 number of transistors. So there is a saving of 4 number of transistors. Okay, so saving some transistors over a fully complementary CMOS is a good thing. Okay, it's advantage, but there is a drawback also. We know that thing. Whenever we use a ratioed circuit, there is a drawback that we need to have a proper sizing of the transistors. Otherwise the functionality will be affected. Okay, so the drawback of saving some transistors here in this case is that transistor sizing becomes a critical in ensuring proper functionality of the circuit. So in this case, the sizing of the transistor should be done with utmost care. Okay? Otherwise, it may not give us the functionality that we intend to do, that we want. Okay, so this will force to increase the sizes of the transistors M5, M6, M7, and M8. Okay, M5, M6, M7, and M8. And what is the relation between like these sizes? Why is it done? And how to decide the sizing of transistors? What is the logical effort? And those things. There are topics for that, and we will come to those topics later on in future. Okay, and since this is drawn in this fashion. Okay, so and PMOS and NMOS are complement to each other. Okay, so in this case, in this type of circuits, we know that static power dissipations are not an issue. Okay, and this kind of memory is not used in data paths, okay, but is a basic building block for memory cell. Uh, then let us see this multiplexer based latches. Okay, these are latches, not flip flops. Okay, so they will be level sensitive. So multiplexer based latches can provide similar functionality to SR latch, okay, but has the important added advantage that the sizing of devices only affects the performance and is not critical to the functionality. So they are done, that same SR latch is done here uh, using multiplexers actually. Okay, using multiplexers. So earlier we had seen this to be done with the help of inverters. Now NOR gates. Now it is done using. It is implemented using multiplexers. So look at this. This is a negative latch based on multiplexer. This one a negative latch. Okay, and okay, this one is a positive latch. Positive latch. Look at this. Uh, let us see. When clock is a 0, it means that this is the select line for this multiplexer. Okay, this is a 2:1 multiplexer. When clock is 0, this input will be forwarded to the output. Okay, and this will become equal to D. Okay, whatever is the value of D, it will come here. It may be 0 or 1, whatever. Okay, doesn't matter. So and D is again fed back to the input side. So D comes here, right? D comes here. When clock is 0, output is D, right? Now when clock uh, goes to 1, when clock goes to 1, what happens? This input will be fed to the output, and this is already D. So this will be coming here, and Q will again be equal to D. Okay, and when again clock goes to 0, this 0 input, that is D, will again come here. D may be anything, 0 or 1, whatever. When it again goes to 1, control line goes to 1. So this D was already fed back to the to this input. So this will again appear here at the output Q. So we see that this is able to latch information from the previous for the from the previous cycle. Okay, and hence it's called latch. But why is it a negative latch? Why is it a negative latch? When clock is 0, input is passing to output. This is the transparent mode. Okay, and when clock is 1, this the previous information is held, is kept tight within the circuit. So this is the hold mode. Okay, so when clock is 0, this is transparent mode. When clock is 1, this is hold mode. Again, when clock is 0, this is transparent, and again hold. So this is what happens for a negative latch. Similarly, this is the case for a positive latch. So here, when clock will be 1, then it will be the transparent mode. When clock is 0, this is hold mode. When clock is 1, again this transparent, then hold. Okay, so it will be just complement in operation with respect to this negative latch. You can very well verify this. Okay. So this is a positive latch built using transmission gate. This was a block diagram. Now this is in terms of transistors. This is in terms of MOSFET, and is built using a transmission gate. And we know that transmission gates are very well, very popular in designing multiplexers. And since this is a multiplexer based design, so we can use transmission gates here. Okay. Look at this. This is transmission gate. Let's name this. This is transmission gate 1 T1. This is transmission gate T2. Okay, so this is a positive latch, this circuit. Okay, this circuit. So let's start with the when clock is 1. When clock is 1 here, when clock is 1, so this clock bar becomes 0 and this clock becomes 1. Okay, so this one logic 1 at PMOS, this PMOS will not conduct. Logic 0 at NMOS, this will not conduct, and but these and these one conduct. So T1 will conduct. When T1 conducts, T2 does not conduct. This is not available. T1 is available. So input at T1. Let's say this is D, so this becomes D bar. Okay. So input at T1, D bar will be passed to the output of T1. So here you will get a D bar. This will be D bar. Okay. And this is again an inverter used here, a CMOS inverter. So Q will become D. Okay. So when clock is 1, output Q is equal to input output Q, that is equal to D, which is actually the value of the input signal. The input signal passes to the output because this is operating in transparent mode for a positive latch. Remember here, look at here. When clock is 1, this is in transparent mode. So this was transparent mode. Transparent means the output is transparent to the input, so that input signal can pass freely to the output terminal. Okay. Now, when clock goes to 0, what will happen? When clock goes to 0, the reverse of these things will happen. The reverse of these things will happen. Remember, it was D here, okay, in the previous cycle, and this is connected here. So the D was available here, and this becomes D bar. Okay, so this was available during the previous half cycle. Okay, now when clock becomes 0, so clock bar becomes 1, clock becomes 0. So this T2 is conducting and T1 is off, T1 is not conducting. So now in this case, when T2 is conducting, the input value, the input signal at T2 will pass to its output, which is actually D bar. So D bar will be available here at the output of T2. And the output of D bar will become again D at Q, because this is an inverter, and this D is again fed back here. So it will be available in the same fashion. So this D is maintained. The value of D is maintained. Okay. Now again clock will go to 1, 0, 1 and 0, and in this way the operation will continue. So it is able to hold the previous data value. Okay. And this operation is this circuit is built using transmission gates, 2 transmission gates. So how many transistors are used here? Look at here, 1, 2, 3, 4. Okay, and 4 plus 2 for this, 2 for this, 2 for this inverters. So 4 plus 6, 10. Total number of 10 transistors are used here. Okay, but here look at since the load to clock is 4. Why? Because the clock is connected. The clock remains same for the whole circuit. Okay, there is only one clock signal, which is feeding to all the different many number of devices on the chip. Okay, so how many transistors are connected to a particular single clock signal? That defines a load for that particular clock signal. So in this case, the clock signal is connected to this 1, 2, 3 and 4 number of devices, so it becomes 4 here. Okay. But we do not want to give more load to a particular signal because that affects the performance. Okay, this you can very well you can relate it to like this. Suppose you are driving a cycle, okay, cycle, not motorcycle, cycle. Now that paddling. So and you when you are driving alone, no, you are not having any load, then it's okay, fine. But when you take a certain load means let's take you also take one of your friends onto your cycle, then it becomes a bit heavy to ride the same cycle. Okay, now what happens when you take two of your friends? Now it has 3 persons sitting on the same cycle, and you are trying to ride the cycle. Now you will require more force to drive the same cycle, which was easier to ride when you were alone. So this is the effect of loading on the circuit also. Circuits also face challenge when the load is increased. Okay, so it is advisable to keep the load minimum for a certain signal for any given signals. Uh, whatever minimum value it can be kept, it will be good. Okay. I think give me. I will just complete here in this slide. Now, so there the load was 4 for clock signal, and this is one more implementation, but this is using pass transistor. Okay, so this is one pass transistor, this is another pass transistor, which is doing the same thing. The same SR latch is being the same positive latch is being built here, but using pass transistors. What was the goal? The goal was to reduce the load onto the clock signal. But here, look at here, because the clock signal is connected to 1 and only 2 number of devices. So here in this case, the load to clock is 2, which is half of the previous example. Okay, so in those terms, it's a better circuit. But what happens when we use a pass transistor? We know the limitation of pass transistor, right? So just beware of those, that it degrades the voltage when it passes it. It degrades by an amount which is equal to its threshold voltage. So the voltage at output would be lower than the voltage at the input. Okay, if this is VDD, you will get here VDD minus VTN, because this is an NMOS transistor. Okay, so after each pass transistor, the voltage reduces. This is a critical factor. Okay, so when you are able to handle this, then it's fine. Otherwise, it may go, all upside down. And this will affect noise margin and switching performance, and will cause, we also know that pass transistors cause static power dissipation. So take care of this. But this is also the circuit which will do the same functionality, positive latch using pass transistor. Okay, now I leave this task onto you to verify this functionality of the circuit, okay, whether this is acting as a positive latch or not. Okay, so you assume clock 1010 and some D value, and for each of these cases, you try to find out the value at each of these nodes, and ultimately you'll find the value of QM bar. And by looking at the relation between QM and D, you will be able to decide whether this is actually a positive latch or not. Okay. Okay. So I stop here, and then we will move from here in the next class. So any doubts? Yeah. If anyone is having any doubts, he or she can ask. And you give attendance in the chat box.